So in the last lecture, we had talked about how can I relate the directional derivatives of a given map between Rn to Rm, provided that the map is differentiable at some point, right? Yeah. So this is lecture 4, right? Yeah. And then we had also introduced the notion of partial derivatives, and then we saw that the directional derivative at some point is sort of a linear combination of the partial derivatives at that point, provided that the function is differentiable, totally differentiable at that point. But throughout the previous lecture, what we had discussed was assuming that the function is differentiable at some point. But what if the function has its partial derivatives, and what can we say about its total derivative? That is, provided that the function has all its partial derivatives, can we claim that the function is also partial derivative at some point x naught? Can we also claim that the function is totally differentiable at that point? So we have the following theorem to analyze that fact, and there is one of the most important theorems in several variable calculus. So it says that let E be a subset of Rn, f from E to Rm be a function, our regular setup be a function, let f be a subset of E. So we are further restricting the domain, nothing else, and x naught in f is an interior point, if all the partial derivatives del f upon del xj exists. Fine, this is something which we required, but furthermore we need something else, and are continuous at x naught, right? So this is the extra condition which we require, that the partial derivatives they exist and they are continuous as well at some point. Then f is differentiable, that is totally differentiable at x naught, and the linear transformation which will define the derivative, the linear transformation f prime at x naught, which is the way we denote the linear transformation which represents the derivative at x naught, is defined as. So intuitively we can guess that this must go along with the fact how we can represent directional derivatives provided that the total derivative exists, right? So it must carry out the same representation in this case as well, right? So defined as f prime at x naught at some vector vj 1 less than j less than n. So we are talking about the coordinates of a vector vj. So we are given a vector v, and you can think of it as v represented being in terms of its coordinates vj. So this is being given as summation j is equals to 1 to n vj del f by del xj at x naught. Fine. You can write it in terms of in just v as well, but I specifically mentioned vj so that because I am using the coordinates as the coefficient of the linear combination on the right hand side, that's why I specifically wrote it as vj. But this, if you have followed the previous lecture, then you know that this basically corresponds to the vector v with the coordinates being vj. Fine. Yeah. So what? So let's prove it. The proof is quite lengthy. You need to carefully observe each step. Proof. So what we actually need to show, okay, so for simplicity, suppose L, now this derivative is also a map from Rn to Rm, that is something which we already know. So suppose suppose L is the linear transformation L applied to this collection of coordinates 1 less than equals to j less than equals to n. This will give me summation j is equals to 1 to n Vj del f by del xj f x naught, right. So it's exactly the derivative which we are denoting as the linear transformation L, and by the definition of derivative, what we need to show, so we need to show that limit x tends to x naught, x is coming from e minus x naught, the norm of f of x minus f of x naught minus L times, one second, yeah, so minus L times x minus x naught divided by norm of x minus x naught is equals to 0, right. This is what we need to show. So this is in compliance with the usual definition of a derivative in terms of a linear transformation. Okay, but let me fix this in terms of the epsilon delta definition. Therefore, or rather I should write equivalently we need to get hold of a delta greater than 0, right, such that this value is less than epsilon, that is norm of fx minus fx naught minus L times x minus x naught divided by norm of x minus x naught, this is less than epsilon, right, for all x such that its distance from x naught is less than delta and x is not exactly equals to x naught. So how can I write it? So I can write it as x being in the ball around x naught with center at x naught of radius delta except x, right. So this is the simple notation of an open ball in a metric space, and we are working in a metric space, fine. So this is what we need to show, but something which you can observe that this is further can be equivalently written as yeah, so this further can be equivalently written as like this, right, fine, yeah. So this is what we need to show. So let me just write equivalently for all x coming from the ball centered at x naught radius delta except the point x, okay, sorry, except the point x naught, not the point x, except the point x naught, I'm extremely sorry, yeah, fine. Okay, now what we are given is that the partial derivatives are continuous at x naught, right, that is something which we are given. Now x naught in f is interior point, right, this is given to us, is an interior point. This implies that there exists some ball centered at x naught of some radius r which is completely contained inside f, right. This is compliance with the definition of an interior point. Now each del f by del xj, where again if you recall these xj's are nothing but the coordinates at x naught, del f by del xj exists and each of them are continuous at x naught, right, exists and continuous at x naught on f, this is what is given to us. But then by definition of continuity, this means that there exists some radius such that whenever x is within that radius around x naught, then these partial derivatives are arbitrarily small, right, that's exactly from the definition of continuity, right. This implies now each of those radius which we will be choosing, that should be less than r, because that is the ball which we have considered in compliance with the interior point which is completely contained inside f, right. This implies that there exists a radius strictly positive, I am choosing a strictly positive such that we can further have the assumption that x is not exactly equal to x naught. If the radius is positive, if the radius becomes 0 at some point, that means that x is exactly equal to the point inside the ball, right. So there exists a strictly positive radius less than r such that norm of del f by del xj at x minus del f by del xj at x naught, this is strictly less than epsilon, but we make some room. We will be seeing that why we make the room in M for all x coming from the ball bx naught delta j. Okay. Now take just take because these xj's are finite in number, so choose delta to be the minimum of these delta i's. Okay. Then what do we get? Therefore del f by del xj x minus del f by del xj x naught, this is less than epsilon by n times m for all x in the ball around x naught with radius delta, and for all 1 less than equals to j less than equals to n. Fine. Right. So till now whatever we have done are just what are just analyzing the things which are already given to us and just bringing them to an epsilon delta approach. That is exactly what we have done. Okay. Fine. Okay. Now let x be a point from this ball. Fine. Right. Okay. So let x be written as x naught plus v1 e1 plus v2 e2 and so on till vn en for some scalars v1 till vn. Fine. Okay. Then what do we have from here? We have therefore what is the norm of x minus x naught? By definition of norm, it is just root over of v1 squared plus v2 squared and so on till vn squared. Right. This is what we have. But this immediately implies that the absolute value of each of these vj's, this should be less than equals to norm of x minus x naught for all 1 less than equals to j less than equals to n. Okay, a sort of intuitive idea that why we wrote it in this form, because since x is in this ball, so suppose this is my ball, this is my center x naught and x is somewhere here, so we can have a vector which represents the line joining x and x naught. That is the thing which we have done. Fine. Okay. Now recall what we require to show. We require to show that fx minus fx norm of fx minus fx naught minus L times x minus x naught, that is less than or equals to epsilon times norm of x minus x naught. That is what we require to show. Now if I further apply the structure of L which we had previously according to the theorem, now we need to show, we are further writing it. So what we had was fx minus fx naught, I can write x as x naught plus v1 e1 and so on till vn en minus fx naught minus, by definition my L was in this form, right, j is equals to 1 to n vj del f by del xj at x naught, right. This was the definition of L which was given to us, right, and this is less than or equals to epsilon times norm of x minus x naught. Okay. I had worked with strict inequality as far as I remember, right. Yeah. So this was what we require to show. Fine. But we can actually further simplify this in terms of each of the components of f, because f is a function from Rn to Rm, so f will have m real valued functions as its components, right. So we can work out which each of those components, and that will be a simpler approach. And furthermore, whenever we talk about each of the components of f, those are real valued functions, then we can apply the mean value theorem to it, right. Fine. So let's quickly see what we do here. Now consider f to be of the form f1 f2 till fn, sorry fm, right? Fine. Therefore each fi is a function from e to r, is a real valued function. Therefore we can apply the mean value theorem to it. We can apply the mean value theorem to fi. How can we apply the mean value theorem to fi? Therefore fi of x naught plus v1 e1 minus fi at x naught, this should be is equals to, yeah, so this should be the derivative times x naught plus v1 e1 minus x naught. So it should be coming out to be del fi by del x1 at x naught plus ti e1 times v1 for some ti between 0 and v1, right? This comes from the mean value theorem, right? But observe that the modulus of this del fi by del xj x naught plus ti e1 minus del fi by del xj at x naught, this should be less than equals to the norm of f, right, in terms of norm of this expression in terms of f, because each of these fi's are just components. So this immediately follows, this immediately follows from the triangle inequality, right? So this is less than equals to norm of, not the triangle, I guess the Cauchy-Schwarz inequality, yeah, right, del f by del xj times x naught plus ti e1 minus del f by del xj x naught, and this was less than epsilon by nm. Fine. Okay. Therefore this implies that fi at x naught, modulus of fi at x naught plus v1 e1 minus fi at x naught minus del fi by del x1 to x naught into v naught, this should be less than epsilon times the modulus of v1 divided by nm, right? Yeah. Fine enough. But then we can sum it over all the m's, right? Summing over all 1 less than I less than equals to m, and since the norm of this is less than equals to mod of y1 and so on till mod of ym from the triangle inequality, what do we have? So yeah, so the m will cancel out, right? We will have that norm of fx naught plus v1 e1 minus fx naught minus del f by del x1 at x naught v1, this should be less than epsilon times v1 by n. And now this will follow for x2, x3, x4 and so on, right? Right. So similarly, I am not writing it anymore. Similarly, the norm of x naught plus v1 e1 plus v2 e2 minus x naught plus v1 e1 minus del f by del x2 at x naught into v2, this should be less than equals to epsilon times. So here I have here I had v1, so here I should have this part cancelled out, so I will have norm of x minus x naught by n, right? Fine. Because the norm of in the previous case here we had written it simply to be the modulus of v1, because the modulus of e1 is just 1, or the norm of e1 is just 1 typically. Fine. So if I continue in this way, continuing, the norm of f of x naught plus v1 e1 and so on till vn en minus f of x naught plus v1 e1 plus vn minus 1 en minus 1 minus, sorry, I closed it up here, minus del f by del xn in this case at x naught vn, this should be less than equals to epsilon times norm of x minus x naught by n. So again, if I just sum over these inequalities, summing over all these inequalities, simply this n will now cancel out. Norm of f of x naught plus v1 e1 and so on till vn en minus fx naught minus summation del f by del xj. This follows from the triangle inequality, and it will eventually give me a telescoping series. That's what's exactly happening here. Right. J is equals to 1 to n x naught vj. This is less than epsilon times norm of x minus x naught. Fine. And this is what we required. This is exactly what we required, right? Yeah. So just go through the proof once or twice and try to fill in the gaps whenever you feel being confused. If you just write it out on your own with some more details, you will get to understand what's happening throughout, right? This is not at all complicated, but there is some deeper notions included. That's why it seems to be a bit complicated. Fine. Okay. Yeah, so we have proved that therefore given a function which has its partial derivatives existing and continuous, then we can say that f is differentiable at that point. As an example, say f is a map from R2 to R2 such that f of xy is x squared plus xy times y squared, then all we need to check is its partial derivatives, right? Then what is del f by del x? So it just here, from here it comes out to be 2x y and 0, and it's del f by del y. This is here, from here I get x, from here I get 2y. Yeah, so both of them are continuous on R2, right? They exist and are continuous on R2, which implies f is differentiable on R2. Yeah, so this can actually help you check the differentiability of a function on some given domain, because the calculating the partial derivatives is much easy. Fine. Now the ways to represent the derivative now, that is quite important. You should now clearly observe it out. Okay. So what we conclusion is that if f is a function from E to Rm and all the partial derivatives of f exist and are continuous on f, then we just conclude that the function is differentiable at that point. And once the function is differentiable at that point, then the function has all its directional derivatives existing. But once we have this scenario, then we recall, then we can represent the directional derivatives as a linear combination in terms of these partial derivatives. So a continuous on f at x naught, then all the directional derivatives also exists at every interior point x naught in f. Yeah, so all the directional derivatives also exist. And how is it given? So the directional derivative at the vector v1 till vn of f at x naught. So this should be just the linear combination in terms of vj, j is equals to 1 to n del f by del xj, right. This we had concluded in the previous lecture, and now what we conclude is that we not only require to be having it totally differentiable, but at the least what we can have is that that all the partial derivatives of the function exist and are continuous. Fine, right. Yeah, now this is sort of a notation which will make things easy. So, notation, this is also something called what we call a gradient. Okay, given a real valued function f from e to r, we denote delta f at x naught to be this vector del f by del x1 x naught, so on till del f by del xn at x naught. Okay, but each of these xi's are basically the coordinates of x naught. Okay, in that case this is something which you can immediately observe, that the directional derivative of f at x naught, this is just the vector what we call the dot product or the scalar product of the vector v with the gradient of f x naught. Fine. Okay, now observe this. So we have the directional derivative written in this way. Fine. And how do we define the total derivative? See, what I am trying to say is the following. Okay, now what we have is that the function, if differentiable at a point x naught, then its derivative applied to this coordinate, this can be written as summation vj del f by del xj at x naught. This is what we have, right? Right. But then this f can be written coordinate wise. So I can write this coordinate wise as vj del fi by del xj, represented coordinate wise as a row vector. So this is 1 less than I less than. So f will have m components, right? But then observe that thus there is a matrix representation to this linear transformation, right? Thus we have a matrix representation to this linear transformation as, so if for each of these vj's we are getting the images in this form, so the matrix must carry out the coordinates in this way, right? So df at x naught, this is just the matrix with the coordinates vectors to be del fi by del xj at x naught, right? And how do we write it basically? So this is just the column vector gradient of del f1 by x naught, gradient of del f2 by x naught, so on and so forth till gradient of del f m by x naught. And how was the gradient written? So it was the dot product of the vector v along with this v1 x1, right? So what we can do is that we can represent it in this way. So this gradient was not the gradient was not the dot product, the gradient was in terms of the partial derivatives. So what should be the gradient of del f1, what should be the gradient of f1 at x naught? It should be the row vector of the partial derivatives in terms of each of the coordinates xi. So this should be of this form, right? Del f1 by del x1 x naught, and I continue till del f1 by del xn x naught, right? Then I have del f2, let me write it a bit bigger. So I have del f1 by del x1 at x naught, del f2 by del x1, sorry, del f1 by del x2, and continuing till del f1 by del xn at x naught, and it will continue, and the last row vector which we will have is del fm by del x1 at x naught until del fm by del xn at x naught, and this is what we call the Jacobian matrix. Fine. How is this Jacobian matrix used? Let me go for a quick example. Just consider the previous example we had considered, f from R2 to R2 such that fxy is equals to x square plus xy and y square. This is what we had. Then we had already proved that it's totally differentiable at every point on R2 because its partial derivatives were continuous on R2. What was the partial derivatives? So del f by del x was it should be 2x plus y and 0, and its del f by del y should be x and 2y. So what we conclude is that therefore what should be my Jacobian? That is dfxy. So it should be so f has two components, right? Yeah, fine. Yeah, so f has two components, so this should be del f1 by del x, del f2 by del x. So del f1 by del x is 2x plus y. Yeah, so I can simply write it as del f by del x along this row vector immediately, right? So I have 2x plus y, del f1 by del x, del f1 by del y. Del f1 by del y would give me x, del f2 by del x would give me del f2 f2 is y square, so this is my f2. So del f2 by del x would give 0, and del f2 by del y will give me 2y. Therefore the directional derivative in the direction of, let's say, some vector vw is just dfxy multiplied with vw, which is just this matrix 2x plus y x 0 2y multiplied by vw. So this will give me the column vector, or whatever you can consider this to be a row vector as well. So this is just 2x plus y times v plus xw and 2yw, right? Or you can write it like this. So this will give me the directional derivative at any arbitrary direction vw starting from an arbitrary point xy. Fine. Yeah, so let this lecture be up till this much. In the next lecture we will talk about the chain rule. Okay, how can we extend the chain rule from what we have seen in the single variable case to the several variable case. So meet you guys in the next lecture.